Welcome to EDU World Space.
Okay, so we're doing chapter 34, problem 43 here. So we have two lenses with focal length of magnitudes 12 centimeters. It says the first is diverging and the second is converging. So this is how I drew it here. You can see that f1 is negative 12 because diverging lenses have negative focal lengths, and f2 over here is positive 12 for the converging lens. It also states that they're 9 centimeters apart here, so I set d equals 9 centimeters. Okay, so we have an object 2.5 millimeters tall, so y equals 2.5 millimeters, and it's placed 20 centimeters to the left of the first lens. And part A asks how far from the first lens is the final image formed. Okay, so this is a multi-step process. So first we just have to find the image location from the first lens, use that as the object location for the second lens, and then find the last image location. So first let's say S1 prime. So we can solve the thin lens equation, which I'll write up here, for S prime. And we see that this is S f over S minus f. So this becomes 20 times negative 12 over 20 minus negative 12. If you plug that in your calculator, we should see that this is negative 7.5. So what that means is that the image from the first lens is 7.5 centimeters to the left of the lens. Cool. So now we need to figure out what S2 is. Well, S2 is how far the first image is from the second lens. So if we're over here, image, which is 7.5 centimeters, then this is 7.5 plus 9 to get to the other lens, so 16.5 centimeters. Again, we can plug our thin lens equation in, and what we get is 16.5 times 12 over 16.5 minus 12. We can plug that into our calculator, and we should see this comes out to being 44 centimeters. Cool. So this is positive, so that means it's to the right of the first lens. So or the second lens, sorry. So if this is 44 centimeters to the right of the second lens, right of lens 2, then to get the actual value we want, which is how far are we away from lens 1, we have to add on 9. So this is 53 centimeters right of lens 1. Cool. Let me label these lenses here. That's 1, that's 2. Okay, so now part B is the final image virtual or real? Okay, well, we don't even have to do any calculations for this, because if we think about the image formed by the second lens, the object was on the left of it, and the image is formed on the right. And that only happens in converging lenses when the image is real. So we automatically know this is a real image, which is kind of tricky because the intermediary image formed from the first lens by itself is actually virtual. But then we get a real image out after going through the second lens as well. Cool. Okay, so part C, last part. What is the height of the final image? Is it erect or inverted? Okay, so first let's do the multi-step process again. So we know that M magnification is negative S prime over S, or Y prime over Y. So we know that Y prime is negative S prime Y over S. So now Y prime 1, this is the height of the image formed only by the first lens. This can be written as negative S7.5 times 2.5 millimeters over 20. So let's plug that in our calculator, and we should see negative 0.5 times 2.5 divided by 20. So this is 0.9375. That's going to be in millimeters. And we can see that it's positive. So that means it's upright. So let's go ahead and do this again for the second lens. So this is negative s prime y over s. So what this becomes is negative 44 times 0.9375 over 16.5. Cool. So let's plug that in. We should see that this is divided by 16.5. And this comes out to being exactly 2.5 millimeters. Huh, interesting. So it comes out to being the same exact size as it was before. So overall, there is zero magnification. It's also positive, so that means we know that it is going to be upright. Is that right? Oh, I left a negative sign over here. I wonder why I was confused. This negative sign right here means our answer is negative. So our actual final answer here is inverted. No magnification, but it does invert.